Let's talk about outliers in this video. And the outliers that we're talking about would be data points that seem to not fit the expected values that you're looking for in your measurements. So a couple of sections in the book are relatively sparse on information, but they're probably the best that we have for this book. And so we're going to be referencing material from outside of the book. Now, just to zoom out again, we have the total overall uncertainty, and the precision uncertainty that we have associated with that overall uncertainty is what we're trying to quantify using statistical analysis. So bias uncertainty, we cannot use statistics on. That's going to be an offset of some sort, and so we use calibration and other methods to take care of that, or at least quantify that bias uncertainty. Whereas the precision uncertainty, we can use statistical means to figure out or quantify what our uncertainty is, or the contribution of that precision uncertainty to the overall uncertainty. So again, we're still down in the weeds of the statistical analysis, and this is one more piece of that puzzle. And we are talking about how to determine if an outlier exists, and if it does, are we justified in removing that outlier? So we've got a problem to solve here. We've flipped 271 fair coins, which means they're not weighted. So we have an equal probability of landing on the head side as we do on the tail side. So recall that rolling dice, flipping coins can be represented by a normal distribution, the Gaussian distribution, the bell curve. And we like that distribution because it's well understood. And we have a table that we can look up the probabilities. And those probabilities then correlate to the uncertainty of a specific measurement. So we're going to try to figure out how we can determine how many mathematical outliers there are. So that sounds interesting, right? So outliers is the general idea. Obviously, we can get more detailed than this, but any data point not expected to be in the data set could be an outlier. So we're going to give some examples of that. This is based on the expected result of the experiment. So we just say, we expect the results to look like this based on the governing equations. And so here's the trend that we would expect. And so these two red dots, we would consider these outliers because they do not fall within this expected range. Obviously, there are some pretty major cautionary tales about throwing data out. And so we don't want to just throw it out. We want to be very cautious whenever we throw out data. Because if we made a decision based off of discarding data and that it actually occurred and it was a true data point, then we would be in trouble because we as an engineer are prescribing maybe material properties or the performance of a system based on our measurements. And if we threw out an outlier that truly was not an outlier, and that could impact the occurrence of what our customer or our design engineer that's using our data is relying on, then we would take on some liability there. This note is really important. Confirmation bias is a huge problem. And the reason I put this in here, I mean, you could zoom out and say confirmation bias in our personal lives is a huge problem. But when we're talking about data, you can just say that, I mean, these data points, they are very clearly outliers. But what if we were saying this data point, we suspected it? Maybe we were confirming, we just see this trend and we're like, well, it would be really convenient if we threw this data point out because then my data would fit a lot better. And we're confirming that bias that we want to remove data so it looks better. And so we want to be real cautious of throwing out data, especially if there could be some confirmation bias happening. So we need to look for objective ways to throw out these results or these outliers. So here are some there's a lot of different topics that we could cover here. I've narrowed it down to just 4 ways to remove outliers. You could know the governing trend and throw away abnormal distant points. And so you can see this trend. We've got something happening here. We're like, oh, well, this doesn't fit that trend. And so this is likely an outlier. Now, what causes outliers? There's a lot of different causes for outliers. It could be that somebody opened the door and the wind blew a different way right here. Or it could be that the instrument was not functioning properly on that specific data point. Or maybe the thermocouple became detached from the data point. There's a lot of things that could cause these outliers, and so we want to be very cautious of throwing them out it's best if we can understand what the trend is and we can understand exactly what's happening with each data point when we're collecting it. So then we can determine whether or not that's an outlier. So that's one way of doing it, just knowing the governing trend, throwing anything out that's very far away. Our book suggests this, that we estimate a 3 standard deviation band from the mean and discard all the points beyond this. And so we're just saying, well, let's put a 3 standard deviation band on here. And this is probably not super, obviously we've got a little bit of asymmetry here, where we've got, it should be that these 2 red bands are symmetric about the mean. So this black line is probably shifted over from where it ought to be. But at any rate, if we say this is the mean and this is 3 standard deviations, we say anything outside those we're going to throw away. So the book does suggest that. There are some downsides to doing something like that. And as we go through, just know that there are different methods and different downsides, pros and cons, or byproducts, or however you want to think of it, to throwing data out. All right, so generate box plots and remove the points beyond the upper and lower quartiles, which is 25 and 75 percentile, 25th and 75th percentiles. So we create this quartile box, and then we say, here's the upper fence, here's the lower fence, and those fences are 25th and 75th percentiles, so anything outside of those. So we could do it that way. Or the way that we have chosen to discuss in this class is Chauvenet's criterion, based on statistical methods to remove points beyond the criteria. So Chauvenet came up with a criteria that says we will statistically determine a point where anything beyond that point or that bound, we are going to assume that is an outlier. So we're going to step through Chauvenet's criteria today. So again, we have kind of excluded this based on expected results of the experiment, and we're going to use statistics of collected data points, the sample statistics, in order to determine which data points are outliers. So how does this work? Well, we find a probability band that is likely to contain all number of samples. So we have to make some assumptions in order to do this. And then if we check each of the data points to see which ones fall outside of that band, then we can remove those data points. And so that's what Chauvenet did. So William Chauvenet was a professor of mathematics, astronomy, navigation, and surveying. He helped found the U.S. Naval Academy, where he taught for many years. But here is why he comes into our discussion today, is he determined a decent method. Now, this is not the end-all say-all. There are many other methods out there. So just know that when you get into a very specialized field, or maybe your employer, or maybe your research lab, there are going to be other methods that people like better given their circumstances. So we're trying to look at the scenarios that a typical engineer may encounter, and we're trying to give you an easy to use tool that will work for most events. But just know that this is not going to work for every situation that you're going to encounter as an engineer. Okay, so here are Chauvenet's criterion. So we have a plus or minus D max. So again, this is that boundary that we're going to set, or a band that we're going to set around the mean. And so if anything falls outside of that band, then we're going to say it's an outlier. So D max is the maximum allowed deviation. Oh, we've seen this before, that deviation. Each individual point, how far is it away from the mean? And since we're using sample statistics here, each point minus the sample mean. So we're seeing that deviation. And then we're going to divide that by our sample standard deviation. And so if it falls outside of this equation here, we're going to discard that and say it's an outlier. So we need to figure out, so in order to find D max, we want to include all observations that we have in the sample that we pulled from the population. We need to find the probability band that includes n minus 1/2. So this is Chauvenet's contribution here, as he set this limit and said number of samples minus 1/2 out of the total number of samples that we have in the sample population. So the probability of that is n minus 1/2 over n. So if we put a 1 in here, because we have n over n, which is 1 minus 1 over 2n, we can we can simplify this down. And what we're looking at here is if we have our Gaussian distribution and we have set these bands, we are trying to identify anything outside of those bands, so out in the tails. And so we're putting a limit, and this is the limit, this 1 minus 1 over 2n, that's the limit. And anything outside of that is going to be what we throw away. So we need to identify what that is. So that's what this variable is the probability represented by one tail. And the reason we're doing just one tail is because we're going to use that same table we've been using to find our z value. And so that has only half of the data set in it. So we can use that z associated with this s from a normal distribution table. That's very handy for us. So this right here, this s equals 1 over 4n will tell us the outliers or anything beyond the band or that limit that we set for the outliers. So if it falls within this s equals 1 over 4n, we're going to discard it. And so that's going to be one of the tails. So graphically or using this figure, this is what we're representing because the table itself only has half of this. We are trying to identify this s on the one side only. So here's our limit that we put. Thank you, Chauvenet. We've got our D max, and so we're saying anything that falls outside of this point, we are going to discard as an outlier. So then D max is equal to our Z value, which is number of standard deviations from the mean. And since we're using table 3.2 and it has only half of the area under the curve contained in table 3.2, then we have 0.5, which is the half of the probability. Because you remember, having a probability distribution curve means that we have 100% of all occurrences falling under the curve, or the probability is 100% that we've captured every data point that is possible using the probability distribution function. And since the table is using half of that, we have half of our probability minus our s, which again is the outside of this. And so we're basically saying we've got half of the probability under this curve, and we are interested in the side outside of this D max that we've set, this limit that we've set. And so that's how we find our D max value. So we're using the Chauvenet's criteria to figure out how many of those are outliers in the data set. So again, this S that we're trying to find is this tail right out here. So we've got 1 over 4n. So if we take our 4 times number of samples, which is 306, we get 1224, which is equal to 0.000817. So then if we go back to that equation there, right here, 0.5 minus our S, 0.5 minus that is 0.4992. Great. So now we can look it up in our Z table. 0.4992 is the Z that we have associated with that D max. And so we've got 3.14. And the reason I have the extra digit out here, this 0.49, is because in a spreadsheet that I have, you can see I had it a little bit closer. I had more resolution in my spreadsheet. So we are 3.149 is what our D max is. And I say this is table 3.14-ish because I cropped it to make it a lot easier for us to look at here. So this is our value for D max. And so now if we put our D max in there of 3.149, and again, we get that from 306 samples, which correlates to an S of 0.00130816. And so our mean of the sample is 5.17. And so we end up with S sub X is 0.601. And so our largest event must be less than our X bar plus our D max times S sub X. And our smallest event greater than that, event greater than this. And so now we have these bounds. And so anything falling outside of these two bounds, we can throw away. So the results in our population defined as laying between 3.26 and 7.05. So where did I get those two numbers? Well, I just plugged in these values right here. So the 3.149 is right here. Our X bar, 5.157, is right here. And our sample standard deviation 0.601 is right here. And so now we can say anything that is a 0 to 3 or 8 to 10 is an outlier, because those are outside of our range. And again, the lower bound here, the 0, is because we have to flip a coin at least once. And so that's the one end, and then we limited the number of flips to 10. So we would discard 65 of our 306 occurrences, which is approximately 21% of our occurrences in this specific example. So you can see it's pretty easy for us to step through this, and this is what it looks like graphically. So we had all the flips, the number of occurrences from those flips. So people who flipped it 10 times and got 3 heads out of 10 flips fit into this bucket right here. So you can see it looks a little bit Gaussian, pretty close to Gaussian, but the important thing that we're taking away here is Chauvenet's criteria says that this is the bound. So anything outside of this bound on the low side, we would say is an outlier. So now you can see we actually have a hard limit of what is acceptable and what is not acceptable based on Chauvenet's criteria as an outlier. And so you can see here's the other bound on the other side. So we throw away these data points. So it makes it very easy for us to throw things away. And like I said in the beginning, it is a pretty good method. It's easy to implement, and it can cover many scenarios, not all scenarios, but it is a pretty good method for us throwing away data and being comfortable with doing so. So that's what that looks like. We end up keeping just what's under the curve here. But this is a very important question. Are there risks associated with this process? Absolutely. Should we repeat the process to detect and remove outliers? We can. We could definitely repeat it, but should we? And so if we repeat it, and so say we remove these and now we have a new distribution, and then we run that Chauvenet's again, are there risks? And the answer is absolutely, because now we're starting to throw away more and more data points, and we're getting narrower and narrower. So we need to be really cautious. I would say a good rule of thumb is do this once, maybe twice, as you're running through the Chauvenet's criteria to determine what outliers are and discarding data that seems to be an outlier based on Chauvenet's criteria. This I just wanted to point out. I noted a little bit ago that this looks pretty Gaussian. And if you think about the central limit theorem, what could we do to make it look more Gaussian? Well, we could take a higher number of samples each time, and then we could take more of those data sets with higher number of samples over and over again. So what I did here is I ran this computer simulated based on this website here. So this is what we had in class. This is just flipping the coin 10 times. We had 809 times that we've done that 10 times, and it looks pretty Gaussian. But what if we flip that same coin 1,000 times? Well, it looks a lot more Gaussian. If we flipped it 10,000 more times, now it looks very Gaussian. And so just think about that when you're collecting data. Do I need to break 5 samples 30 times? Or should I break 30 samples 30 times? And the more times you can get, higher number of samples you can get, and the more number of times you could take those samples, the more Gaussian that's going to look based on our central limit theorem.